Okay, so today we're going to consider limits where we take our variable to extend out to infinity. And then our kind of interest is to see what happens to functions as our values either go to infinity, our x values go to infinity, or negative infinity. So let's first define what kind of give a definition to what limits that tend to infinity that exist. So if we say let f be a function defined on some interval from a to infinity. So here we're saying who cares what a is? I mean, as long as we're going out to infinity. So this is our focus is going to be as x goes to infinity. So then we could say the limit as x approaches infinity of f of x equals to L. This means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. So basically what we're saying here is, look, if x becomes really, really large, f of x will get closer and closer to L. So what we notice in this case is as x becomes large, my function settles down to some value. And if you think about this, this is something that we have seen in analysis. It's just we never expressed it this way. So think of it this way. If I have a function where this is L, so by definition, what am I claiming? In the long run, my function is going to approach this line. And you know what this is, right? I mean, you've seen this in pre-calculus, and this is kind of what we define a horizontal asymptote, isn't it? So if you think about it, what are we saying? As x goes to infinity, my function approaches this line. So what if I have a function that kind of has this motion? But what do I know? Eventually, in the long run, as x gets large enough, this is going to start settling down to L. So here you could see what's happening. As x becomes really, really large, f of x itself starts settling down to L, which basically in this picture, L is my horizontal asymptote. So you could see why in this section this is titled limits at infinity and horizontal asymptotes, because technically speaking, if we have a horizontal asymptote, then we basically, that means as x goes to infinity, our function settles down to that horizontal asymptote. And same thing is true for x going to negative infinity. So we could say, look, down here we could say, notice as x goes to infinity, we have f of x approaches L. So what does this imply? The limit as x approaches infinity of f of x, that just equals to L. Okay, so just keep in mind that, I mean, we will define it in a minute anyway, but we could see that taking the limit as x goes to infinity, and same thing with negative infinity. In other words, we're finding horizontal asymptotes. So in this class, and from this point on, if you're asked to locate horizontal asymptotes, you just have to evaluate the limit of that function as x goes to infinity. If it settles to a number, then great. That means that's a horizontal asymptote. If it doesn't settle to any numbers, like see this one doesn't have a horizontal asymptote as we go to the left. as x goes to negative infinity, this guy goes up forever. So this doesn't have a horizontal asymptote as x goes to negative infinity. So what's important is, if I ask you to check horizontal asymptotes, you need to check both sides, okay? So we'll talk about why you need to check as x goes to infinity and negative infinity in a moment, okay? So let's define the limit as x goes to negative infinity, and then we can talk about horizontal asymptotes, and then we'll just do a bunch of examples here. So we could say let f be a function defined on some interval negative infinity to a. Then the limit as x goes to negative infinity of f of x equals to L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large negative. So this is practically saying the same thing as what we talked about earlier, except now we're going to negative infinity. So, as far as the picture goes, I'm not going to draw a visual for this because it's practically the same thing as above. So let's make a note of that, and then I'm sure you could visualize it yourself. This will be the same picture or similar picture as above, would work for this, except we want x goes to negative infinity. So it's kind of like the picture's flipped. Okay, so I'm not going to spend time drawing that out because I'm sure you can make sense of what's going on. But all this is saying is, as x goes to negative infinity, my function approaches a y value called L, which you can see that's another way of saying it's a horizontal asymptote. Okay, so let's now define a horizontal asymptote officially. So here's what we could say. The line y equals to L is called a horizontal asymptote of the curve y equals to f of x if either the limit as x approaches infinity of f of x equals to L, or the limit as x approaches negative infinity of f of x equals to L. So what we're saying by definition is, look, if horizontal asymptotes of a function exists, then when you evaluate the limit as x goes to infinity of this function, or negative infinity, one of these two, at least one, might needs to exist. Okay. Now, what's interesting about this is, see, last year in pre-calculus, you noticed that, look, if I have a horizontal asymptote, it's usually one. So whether you go to infinity or negative infinity, they'll both be the same horizontal asymptote. But if you think about it, not all functions are like that. Okay, so be careful when you're asked to check if a function has horizontal asymptotes. You need to check both limits separately. So you need to take the limit as x goes to infinity of f of x, as well as the limit as x goes to negative infinity of f of x. Now, there will be time where both limits will give you the same horizontal asymptote. There will be times where one of the two limits will be non-existent. That means it'll go to infinity or negative infinity, and the other one will work. Or there will be times where both limits give you two different horizontal asymptotes, and or you might not even have any horizontal asymptotes, and both will go to infinity or negative infinity. But the point I'm trying to make here is consider the graph of tangent inverse. See, we know that the graph of tangents looks like, so if I talk about the tangent of x, we know that the graph of tangent looks like this, okay? Now, if we are talking about tangent inverse, remember what happens to tangent inverse. The x and y values are swapped because, of course, it's the inverse of tangent. So we could say, notice that f of x equals to tangent inverse of x has a graph of the following. So if you remember, tangent had vertical asymptotes at negative pi over 2 and pi over 2. Now, tangent inverse is actually going to have horizontal asymptotes at pi over 2 and negative pi over 2. And if you remember, the graph of tangent inverse looks like this. And what do you notice? We can say the limit as x goes to infinity of tangent inverse of x, that's pi over 2. And the limit as x goes to negative infinity of tangent inverse of x is negative pi over 2. So what do you notice? This has two different horizontal asymptotes. Now, if I only checked this one and said, look, as x goes to infinity, this has a horizontal asymptote at pi over 2, therefore, that's the only horizontal asymptote, I would be incorrect, because as x goes to negative infinity, you get a different horizontal asymptote. So you need to make sure that you check both sides, okay? So let's go on to, and when I say both sides, you need to make sure that it goes to infinity and negative infinity. You have to check both limits for all functions, okay? So let's go on to our first example. We could say find the limit as x goes to infinity of 1 over x and the limit as x goes to negative infinity of 1 over x. So what do we notice here? We could say, look, notice as x increases or even decreases, so for this case x is increasing, for this case x is decreasing, 1 over x actually goes to 0, because what you notice is when your denominator becomes larger and larger and larger, 1 over a larger number becomes smaller. So if this is getting infinitely large, if x keeps getting larger and larger and larger, then 1 over x keeps getting smaller and smaller and smaller. And the smaller you get, the closer you get to 0. And for the negative infinity case, it's the same thing. If it gets smaller and smaller and smaller, or if you think about it, if it's negative 10, negative 20, negative 30, what's happening, this is getting closer and closer to 0, except the difference between these two is this is a small positive number. This is going to be a small negative number. So basically, if you think about it, if I were to make a table just to kind of clarify it, if I plug in, let's say 1, I get 1. If I plug in 2, I get 1/2. If I plug in 10, I get 1/10. If I plug in 1,000, I get 1 over 1,000. And you could see what's happening to the y values as x goes to infinity. Now, what if I take x going to negative infinity? Like if I plug in -1, it's -1. If I plug in -5, it's -1/5. If I plug in -10, it's -1/10. If I plug in -1,000, it's -1 over 1,000. So what we notice here is, you could say, look, as x goes to infinity, my y values, or 1 over x, goes to 0. And as x goes to negative infinity, my y values, which is the 1 over x, goes to 0 as well. So we could say the limit as x approaches infinity of 1 over x is 0, and the limit as x approaches negative infinity of 1 over x is 0. So what happened is 1 over x has a horizontal asymptote and only one horizontal asymptote, which is at y equals 0. And in this case, what do we notice? As x goes to infinity, as I go to the right, this guy approaches 0. And as I go to the left, this guy approaches 0. So in this case, my horizontal asymptote ended up being the same for both cases, right? We only have one horizontal asymptote, and from both sides, it approaches by horizontal asymptote. But remember what I said, that's not always the case. So you need to check both cases. Okay, so now that one example we did is going to get us into this next theorem, which is nice because it allows us to generalize that statement, or example one, we can generalize it for a bunch of other conditions or other cases. So we could say, look, if r is greater than 0, is a rational number. So all we're saying is r is some positive rational number. Then we could say that the limit as x approaches infinity of 1 over x to the power of r is always going to be 0. So if you think about example 1, r was 1, right? It was 1 over x. But all we're saying is if r is any positive rational number, so this could be, I don't know, 1/2, or this could be 5 or 7. I mean, of course, the larger the power, this means it's x to the power of r is increasing faster and faster. So as x goes to infinity, this will eventually settle down to 0. So anytime you have anything of the form 1 over x to some positive rational number, if you take the limit as x goes to infinity, this is always going to go to 0. Okay, so that's a nice result we get here. So this theorem will be pretty helpful for us. Now, also, we could say if r is greater than 0, this is a rational number such that x to the r is defined for all x, then limit as x goes to negative infinity of 1 over x to the r equals to 0. So look, you're wondering, well, why am I kind of rewriting this again? Well, this makes a big difference because look, r is supposed to be a positive rational number. Why do I need to make a separate statement for this? Well, first of all, this is the limit as x goes to negative infinity, which is different than limit as x goes to infinity. See, over here, r could be anything. See, if r is 1/2, in other words, what am I saying? 1 over the square root of x. And when will I run into a problem for the square root of x? When my x values are negative. But see, as x goes to infinity, I'm not concerned about square root of x because as you're going to infinity, these are becoming just, they're always positive. They're just becoming larger and larger and larger. But down here, if r is 1/2, I have square root of x. What's the problem with this? As x goes to negative infinity, my x values are negative numbers, which would make this undefined. So that's why we're saying, look, if r is a rational number such that x to the r is defined, or this exists. So in other words, we're saying as x goes to negative infinity, just make sure that x to the power of r exists. If it exists, then anything of the form 1 over x to the r will also be 0. Okay, so anytime we have something of the form of 1 over x to any power, as long as r is a positive rational number, as x goes to negative infinity or infinity, these should go to 0. Okay, so let's look at a few more examples, and then basically that should wrap up this section. So remember, the main idea of this section is finding limits as x goes to infinity and negative infinity. So let's take a look at this one. Evaluate the limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Now, here's the problem. I can't plug in infinity for x, right? Because if I plug in infinity for x, what am I getting basically? I'm saying infinity divided by infinity. And see, infinity is not a number. I can't, so this would be a big no-no. If I plug in infinity and say, look, this becomes infinity over infinity, they cancel each other out, and I get, I mean, it's kind of like, what? What does that mean? That makes no sense whatsoever, because remember, infinity is not a number. So when you cancel these out, you're basically saying that it is a number, but infinity is not. So we need to kind of find a way of manipulating this. Okay, so right now I'm stuck. I can't do a direct substitution because after all, infinity is not a number for me to be able to substitute. So what we need to do is, for this problem, we need to use an algebraic manipulation. And here's the trick. See, since this is a fraction, we know that we could multiply anything to the numerator as long as we also multiply to the denominator. So here's the trick. The trick to evaluating this limit is to divide the numerator and denominator by the highest degree of the denominator. Okay, so don't be concerned about the numerator. So what I'm going to do is I'm going to look at the denominator and say, look, when I have a rational function such as this and my limit as x is going to infinity or negative infinity, it doesn't matter as long as it's an infinite limit. I basically say, look, looking at this, look at my denominator. What's the highest degree of my denominator? It's a degree of 2. So what I'm going to do is I'm going to multiply or divide top and bottom, the numerator and the denominator, by x squared. Or in other words, I'm multiplying the numerator and denominator by 1 over x squared. So if I have the limit as x goes to infinity of 3x squared minus x minus 2 all over 5x squared plus 4x plus 1, what I'm going to do is multiply top and bottom by 1 over x squared. And see, that's a valid move. I'm allowed to do that because as long as I'm multiplying to the numerator and denominator, there's nothing wrong because technically speaking, I'm multiplying everything by 1. And anytime you multiply something by 1, you get the same thing out of it. So let's now distribute and see what happens here. We get the limit as x goes to infinity of this becomes 3x squared over x squared minus x over x squared minus 2 over x squared all over 5x squared over x squared plus 4x over x squared and plus 1 over x squared. Now let's simplify as much as we can. So this becomes the limit as x approaches infinity. The x squareds here cancel out, so I have a 3 minus one of the x's cancel out here, so that's 1 over x. And then here I can't simplify that, so it'll just be minus 2 over x squared. All over, this becomes a 5 plus 4 over x plus 1 over x squared. Okay, now look at what's happening here. If you look at the theorem we talked about earlier, which is this one, and we have this here. Now look, the limit as x approaches infinity of a constant is always a constant. But what do we know? The limit as x goes to infinity of 1 over x, what does that go to? That goes to 0, right? We just talked about it. And the limit as x goes to infinity of 2 over x squared. And see, I don't care if my numerator is of a constant other than 1. It doesn't have to be a 1. But as long as it's fixed, and 2 is fixed. So eventually, x squared is going to become so large where 2 divided by a large number, or even if the top number is 1,000, who cares? Because my denominator is constantly getting larger and larger and larger. So eventually, this is going to be forced out to 0 as well. And then the 5 is going to stay a 5. what will happen to 4 over x? 4 over x will go to 0, because as x goes to infinity, this will go to 0. And 1 over x squared will go to 0. So notice how that theorem we talked about is kind of at play here. So what do I end up with? 3 will be 3. This is 0, 0, 5. So what I basically get 3 minus 0 over 5 plus 0 plus 0, which is just 3/5. So in fact, what do I notice? That rational function that we just talked about, we found this horizontal asymptote goes to 3/5. Now, with that said, I want to point out that from this point on, when I ask you to find horizontal asymptotes, you always take the limit as x goes to infinity. Always. You don't. I don't want to see other ways done, because this is the best way to approach it. Okay. But anyway, we indirectly found the horizontal asymptote of this function for this problem. Okay. But we evaluated the limit, so now we're ready to move on. So now let's take a look at example 3. And we could say find the limit as x goes to infinity of rad x squared plus 1 minus x. Okay, so once again, what's the problem with this? I can't do a direct substitution, because if I substitute, what am I getting? Infinity minus infinity? Once again, that makes no sense. I can't say infinity minus infinity is 0, because infinity is not a number. So I need to manipulate what's going on here. So what the nice thing is, if you look at example 2, if we had a fraction, then we could use the trick from example 2. So here's what I could do. I could write this as a fraction. I could just put it all over 1. So what's the trick? Well, I'm sure if you look at this limit, and remember if we had binomials with square roots, what was one of the tricks we used in section, I believe it was section 2 or 3, somewhere around there. We multiplied the top and bottom by the conjugates. So let's try that out, because if I multiply by the conjugate, that puts variables in the numerator and the denominator, which then I could probably use example 2's idea to finish off this limit. So we could say multiply the both numerator and the denominator by the conjugate of square root of x squared plus 1 minus x. So if I do that, here's what I have. The limit as x approaches infinity of square root of x squared plus 1 minus x over 1. So I'm multiplying top and bottom by square root of x squared plus 1 plus x. Square root of x squared plus 1 plus x. And so what does that give us? We get the limit as x goes to infinity. If I multiply this, remember the middle terms I don't care about, they cancel out. So I get x squared plus 1 minus x squared. Okay. Over what happens to the bottom? Square root of x squared plus 1 plus x, which gives me the limit as x approaches infinity of 1 over square root of x squared plus 1 plus x. Okay, now look, what's nice about this, I could use the trick of example 1. How come? Because remember, or not example 1, sorry, example 2. Because the trick was multiply or divide numerator and denominator by the highest degree of the denominator. So see, what happens is I introduced variables in my denominator. And anytime you have limits as x goes to infinity or negative infinity, you could consider that trick where you divide the numerator and denominator by the highest degree of the denominator. So if you look at the denominator, what is the highest degree? I hope you don't say degree is 2, because this x squared is inside of the square root. And what's the square root of x squared? It's just x. So the degree of the denominator is 1. So what I want to do is I want to divide top and bottom by x, or multiply by 1 over x. So what does that give me? It gives me the limit as x approaches infinity of 1 over x all over square root of x squared plus 1 divided by x plus x over x. Now, here's what I want to point out. I can't divide this x with the square root of x squared. How come? Because this x is not inside of a square root, and that is. So we can fix that because what do we know? Can't I write x as a square root of x squared? Which I can because let's come off to the side. Isn't square root of x squared the same thing as x? So what I'm going to do is I'm going to replace x here as a square root of x squared. How come? So then I could use the property of square roots. See, we also learned earlier that square root of a divided by square root of b. I could say that's the same thing as square root of a divided by b. Since they're both square roots, I could just put the square root on the outside and divide these guys out. So right now, I can't take this inside of the square root because it's not written as a square root. So I could kind of substitute in place of x, write it as square root of x squared. So if I come down, I could simplify this as the limit as x goes to infinity of 1 over x divided by, this would be square root of x squared plus 1 divided by square root of x squared. Notice how this is still the same thing as that. They're not changed. These two are still the same. They haven't changed. Square root of x squared is still x. So I'm not changing the problem up, but I'm just doing something to help me out. And of course, x divided by x, that just becomes 1. So now I could say this becomes the limit as x approaches infinity of 1 over x. Now I could write this as one single square root. So it'll be square root of x squared plus 1 divided by x squared plus 1. Now what I could do is I could divide this x squared out to each one of the terms in the numerator. Remember, I need to divide this to everything in the numerator. All right? So I have the limit as x goes to infinity of 1 over x divided by x squared divided by x squared is 1 plus 1 divided by x squared. That's just 1 over x squared. I can't really divide those out. But remember, this x squared needs to divide to everything in the numerator. Then I'll get a plus 1. Okay, so now let's send x to infinity and see what happens. As x goes to infinity, what happens to 1 over x? 1 over x goes to 0. Okay, what happens to 1? That stays constant. What happens to 1 over x squared? That goes to 0 as well. And then what happens to 1? That stays constant. So what do I really get? I get 0 divided by square root of 1 plus 0 plus 1, which what does this become? 0 divided by 2, which is 0. Okay, so this limit is actually 0 as x goes to infinity. Okay? So let's move on to one more example. Now, let me make a comment here. One comment I want to make. The limit as x goes to negative infinity of e to the x, what would that be? Well, we know e to the x goes to, as x gets larger, e to the x gets larger. But as x goes to negative infinity, this becomes a fraction, which, by the way, should be 0. Okay? So think about this. But that's the limit as x goes to negative infinity of e to the x is 0. And in fact, if you look at the graph of e to the x, what does the graph of e to the x look like? Like this. So as x goes to negative infinity, this guy gets closer and closer to 0. As x goes to infinity, this guy goes up to infinity. So notice how this guy, as x goes to infinity, no horizontal asymptote. But as x goes to negative infinity, it does have a horizontal asymptote. So the last example will be pretty straightforward if you know what you're doing with it. If you don't, it might take some time here. So find the limit as x goes to infinity, which is of x squared minus x. So once again, see, if I use direct substitution, I will get infinity minus infinity, which then I can't say that's a number, right? It's not 0. It's like in example 3, it just so happened that it became 0. But anytime you have infinity minus infinity or infinity divided by infinity, we don't know what the outcome is. Now, for this one, as far as the conjugate goes, you could try it out. It'll be a problem because you'll kind of end up back to where you were, because notice how I don't have any square roots. So probably the conjugate idea is not a good approach here. However, this is much simpler than the other examples because, look, notice how I could factor something out, can't I? If you look at these two, what do they have in common? So anytime you have infinity minus infinity, one thing you should consider is if you have square roots, conjugates are the way to go. If you don't have square roots, see if you could factor, because factoring might be to our advantage. Because look at what happens to this. If I factor out an x, what do I have? X times x minus 1. Now look at what happens here. This becomes, if I think about this, if as x gets larger and larger and larger, what happens to this guy? This guy becomes larger, which is infinity. Okay, and what happens to this guy? Well, if a really large number minus 1 is still a really large number, and this also goes to infinity. Now look, I'm no longer subtracting. What's a very large number times a very large number, right? Because I'm saying x times x minus 1. So a very large number times a very large number becomes even a bigger number. So what I'm basically telling you is infinity times infinity is going to be infinity, right? Because all we're saying is a large number times a large number is a large number. So we're not saying that this limit exists. In other words, we're basically saying, look, you have something like infinity multiplied by infinity, which we're saying a large number times a large number gives me just infinity. So in other words, we're basically saying it does not exist anyway, right? So um, this notation here, I mean, this is a little weird because remember, we don't, infinity is not a number, but in the case of multiplication, all we're saying is a very large number times a very large number results in a large number. Okay, so just keep in mind that whenever you have infinity minus infinity, you can't say, oh, this is 0. That makes no sense. Or when you have infinity divided by infinity, you can't say it's 1 because it could be anything. Okay, so the point I'm trying to make in multiplication, all we're saying is a large number, a very large number times a very large number itself becomes even larger. So in this case, we get infinity. Okay, so clearly this limit does not exist. Or speaking in terms of horizontal asymptotes, the graph of x squared minus x has no horizontal asymptote as x becomes larger and larger and larger. Okay, so that basically wraps up this section. Just to quickly summarize it, all we did is we evaluated limits as x went to infinity and negative infinity of functions, okay? And graphically speaking, those limits that we evaluated, we were also finding its horizontal asymptotes, okay? So make sure to come by with any questions you may have.